All right, ready to get started? 6:59. All right. I'll wait till 7. Oh, I should actually turn this off. Input. Go. Right. 7 o'clock. All right. Hi, everyone. Evening. Welcome to this meeting of the Warren Astronomical Society. We are live at Cranbrook Institute of Science. So do we have any first-time attendees tonight? We do. Hi, how'd you hear about us?
I'm 5 years ago.
Yeah, that was me when I joined too. All right, so did you?
Joke, me time.
Oh, it's dark. Well, you got a new one over here. Hi there. So we have an observatory at Walcott Mill Metro Park. We do a free star party every fourth Saturday of the month. We'll be talking about that later, which is really cool. So you can join or renew your membership right here, or you can do it online, via PayPal. So as a tradition, we like to go through the ranks and say your name, so just to get a record of who's here. So hi, I'm Bob Tremblay, president. Yeah.
Dale Timmy, editor.
Dave Baranski, treasurer.
Lemire, new member. Bob Vernon. I'm senior, so it's gonna be what, 22, it was a thing for $9 for the others.
Mary Federico, Marty.
It's gonna be like $31.
Charles Strackmine, secretary.
That's what cloud outreach.
Art gets here. Jim Ayers.
David Williams, the friend of Marty. 31. 22 and John Newmark.
Tom Ferdinand.
John Rasmussen.
All right. Well, hi, everyone. Okay, so we got elections happening next month, both national and here. So if anyone would like to, if anyone's interested in running for a position, see Mark Kade here. Mark, I guess I'm running for president again, so I just saw you. Yeah. If anybody would like to be on the board, let him know. So WASP wearables, t-shirts, and such are available. You can see the selection in our newsletter. And again, Mark Kade can get those for you. Our banquet speaker is going to be Nicole Zellner. Our banquet is when? December what? I'm sorry?
5th.
5th. Okay, the 5th. She is a volunteer NASA JPL Solar System Ambassador, works at Albion College, and she works on studying lunar samples. But she's got a whole huge range of things that she could talk about, and it was real tough picking from the 5 she gave us because we wanted like all of them. Our calendars, are they here? Okay, our calendars are available and they are here tonight. You can pick up your calendar. We have their astrophoto calendars, taken with pictures taken by our members. GLAC, that is the Great Lakes Association of Astronomy Clubs. They are the people that put on the Astronomy at the Beach event from a couple weeks ago. They meet the second Monday, and if you're interested in helping plan and organize astronomy at the beach, they're the ones to talk to, and they need your help, and they're probably going to need new officers come January. So I am going to kick off with, we're going to do a memorial to Marty Kuntz. So let's start that off. I will get this thing back over here. And unfortunately, I don't think I can project this because this is coming from the lectern PC.
Yes.
Sorry.
It's all right. As we're rolling, scrolling, I think probably pretty much everybody's at it.
Where is it? System PC.
That's 28.
There it is. All right. But these people we will see anyway.
Gotcha. Well, my name's Carl, and welcome to my living room. So I essentially live here. So I'm Cranbrook staff. I'm not kidding. I spent a lot of time reading in here, getting away from staff. This is where I hide. So you guys are in my living room, so to speak. And thanks for coming to your meeting tonight, but also for allowing me to come up here and talk about Marty for a minute. Marty was a member of your group and an avid astronomer. He had astronomy radio FM that he loved to do. It's funny, when I first met Marty in 2002, he told me that I think at that time he didn't have it quite yet, but he was thinking about doing a radio show. Eventually became an internet hosted radio show that he did on astronomy topics. And, I'd always kind of tease him a little bit about it, like, oh, Mr. DJ, spin this disc for me. And one time he was running late to get to where he had his setups at his home office, and he couldn't make it to his home office, and his radio show was going to start in like 10 minutes. There's no way he would have made it. So he asked if he could use my office login and do that. So here at Cranbrook, so we had offices down the hall. So he gets onto my equipment, and I actually decided to stay and listen to him. And I will tell you that I was really impressed with what he sounded like a professional DJ. I was amazed at, and he was so knowledgeable about astronomy. It was pretty incredible, because otherwise everywhere else he was pretty confused. Just kidding. Loved Marty very much. We were friends. We go back a long ways. That cannon that you see right there, he was an instrumental team member in actually taking that from the Detroit River, taking the rust off of it here on display at Cranbrook for the general public, and then taking it to Dawson where it is currently on display. He was a very instrumental person in that renovation of that cannon and part of our history. He was also a vampire. So I expect him back tonight at some point. Actually, Marty passed away in April, and I just wanted to say thank you too. I know that you guys did I didn't really see it, but I heard a lot about it, that you did a really nice retrospective for him, and I thank you for that. That's lovely. Marty was very cherished on our end. He was part of my crew for a lot of years here at Cranbrook in exhibits. He was a very talented exhibit maker with a lot of great ideas. And at times he could be a heck of a curmudgeon, but other times he had a great sense of humor, and I enjoyed having Marty around for a lot of things. As a matter of fact, we went on a lot of adventures together, including the bars in Pontiac, which you see there. And so anyways, this picture was from Flat River, Michigan, Greenville. That's from Detroit. So we made our rounds together all over the place. Anyways, I know that Marty has some other friends here too, and family tonight. Mary, his cousin, and Dave and Jim and Janet were close friends of his as well. So if any of you want to come up and say something to Marty about Marty, that'd be great. Yes.
I'd like to say.
Sure, that'd be great.
History, Marty and I, as far as this club is concerned. Tell the story.
Absolutely. I love that. That'd be great. Marty didn't want anything done. I said, well, that's not going to happen. It's going to.
No.
The thing is, we did it in October, your October meeting, because he was a Halloween fanatic. In October was his month. Perfect.
My name is Ken Burton, and I was past president of the club. But what happened with it in the late 90s, early 2000, there was an individual in our club who was not the nicest person you ever saw in your life, and used to give presidents of the club grief all the time. I won't mention his name, but we had all kinds of issues with this guy. And the president, the guy who was president, resigned because of the amount of abuse that he was getting from this particular individual. He was getting phone calls at midnight, people that he didn't like, this guy was doing. But the story goes that the club was falling apart. This is just about the year 2000. And Marty and I said, let's pull the club back together. Let's do it. Let's take it over. And Marty became president and I became vice president. And what we did is we took one of the people. We asked the individual that was giving the trouble, we don't want you back here anymore, is what he did. And there was another fellow that was giving him rides all the time, or he was getting rides from him. And we suspended the guy when he wouldn't stop bringing this guy around. And the club took off right from there. And it was because of Marty's aggressiveness in making sure that the club stood on its own and expanded enormously during that period of time as far as members and such. But it was a lot of Marty and a little bit of me, but it was mostly Marty. And we pulled the club back into thing, and it was because Marty said, it's time that you and I take over this club and get it going. And I'm forever indebted to him, as we all should be, because this club is still existing now and a nice membership and everything like that, specifically because of Marty.
Yeah, I actually, I'm embarrassed to say I didn't know Marty all that well. We didn't go places together and hang out, but he is probably one of the first people I met when I joined the club in 2011. And he was a regular fixture here at the Macomb, or I'm sorry, at the Cranbrook meetings and out at the observatory. And I mentioned this in a newsletter back. The one thing that I do remember is that we were running a scout thing here. We were doing a walk the solar system down this hallway back here. And I got a little excited when it came to how big and far away Jupiter was and used frickin', and Marty was like, "Ah, kids, please." So that was pretty humorous. Anybody else have anything to say about Marty? Please.
Hi, my name's Jim. I think I know most of you, or a lot of you anyhow, but when I joined the club in 2019, right? 2000, I think it was 2001 or two, Marty was president at that time. And I recall Marty throughout the years. I went on to become treasurer of the club 2 or 3 years later, and met a lot of you folks then. But it was something that Marty said at a meeting in probably 2003 or 4, which led to a even greater friendship between Marty and I. He was talking about this observatory in Lake Angeles, Michigan. And I thought, what in the heck's he talking about? It was the McMath-Hulbert Observatory, a place I had visited when I was 13. I'm 87 years old now. When I was 13 years old in 1949, I had visited the McMath-Hulbert Observatory as with a bunch of Boy Scouts. And if it hadn't been for Marty mentioning that, I had no clue that the place still existed, even though it's only like 3 miles from where I live. So it was because of Marty that I heard about the place, and I went over and connected myself with that organization, which still exists, and Marty was part of that. Marty joined us as an active member again about 5 years later, and every Saturday, Marty and the rest of us would get together over at the observatory, work together, and work on projects and stuff like that. But that's where I knew Marty from more than even this club. So God rest you, Marty.
Thank you, Jim. Anybody else?
Yeah.
So Marty was I'm missing Marty because he helped us out quite a bit. Especially in the last few years. Whenever I needed someone to help me with the big job, Marty was the guy. He most recently fixed the lights on our trailer. Man, I'm sure glad he got it done, because otherwise we wouldn't have a trailer. But I joined the club, I think, in 2013, so you'll have to help me with the timeline, but it was right out there in the parking lot. We were doing some solar thing. I was a partial eclipse, probably in 2014. I was pretty green, solar Marty, right? So he was there. I get bored talking to Marty, and I'm probably pulled up an app on my phone or something. It's like, well, Jupiter's there, but it's daytime. He goes, no, you can see it if we get on it. And so we looked up right ascensions and declinations, no computers, and we were scanning, and eventually we found it. If you've never seen Jupiter in the daytime, it's all hued blue. It's a really unique thing. And so Marty made that happen for me. And it's just, I don't know, that's the kind of stuff you get in a club like this. So really cool guy.
Yeah, we'll miss you, Marty. Right. Let's see, back to that. All right. Getting back to our regularly programmed content. Okay, first of all, I would like to apologize to the Kaplans about starting the presentation at the Macomb meeting a little bit early. They got there because at 8 o'clock, we're expecting the presentation to start, and it had already been going for about a half an hour. So we got to do something about filling some time or change the schedule online or something so that doesn't happen again. Sorry. So I have a request for a lecture from somebody who wants to do a lecture. The executive summary is it's about radio telescopes. How do you go from that antenna to the rotating pictures of asteroids that I've seen? I don't know the first thing about that. You know, like what's the hardware and software involved, the data formats, that kind of stuff, if you want to get down deep into it. And is there something like a CCD for radio telescopes? How does all that work? I don't know. So if anybody wants to do a lecture about that, that'd be great. Dale, are you here? Hi there. Okay, Dale Parton, our first VP. I know what he's gonna say.
Yes. Short and sweet. We're doing good on speakers who will talk for a full-length presentation in an hour. We're booked up into February. Right now, what I'm having the most trouble finding is speakers to give a short presentation.
I got one.
Good. I need one for December. Okay. Boy, that was quick, right?
Yeah.
Back to you.
All right. That worked. Thanks. Hey, Riyadh, how's the observatory going?
Yeah, hi. The observatory is doing well. Last open house, which we had recently on the 28th last month, it clouded out, unfortunately, but we still had 6 visitors. So we talked a lot about astronomy in general and about the club and about joining the club and what we have in the observatory benefits and so on. So we were there from about 7:20 to about 8:40 when everybody left, and it was kind of cloudy and raining, so not many other people showed up, and that's understandable, of course. Next open house, hopefully we'll have clear skies, and it's scheduled for October 26th, starting at 7:30. Hopefully we'll see everyone there. We have a lot of equipment to look through and use, so everything is working well, and including the dome. So hopefully we'll see everyone out there. Thank you.
Thank you. David, what is going on with membership and in the bank?
Okay. All right, so kind of a top off. Yes, we have cash. In the checking account, we've got $22,857. PayPal, we have zero. The reason it's at zero is because we had to purchase 2025 calendars at the cost of $682. We had $400 in PayPal, and PayPal, just to fill up that 682, took out 280 from our checking account. So that's why PayPal is at zero. We've also had some deductions during the current month or last month. We had our yearly insurance of $1,480. We also had a $20 pay for Michigan State Incorporation, so that got done. GLAC, we paid $400 for the 2 tables there. Cash box, you got about $500 and a bunch of change. And tomorrow we're going to be writing a check to Jeff McLeod for the picnic that he brought with him, or that he did there. And that's it.
All right. Thanks. Secretary Charlie, what you got for us? Good evening, everyone. Wow, what a great crowd here. My name's Charlie Strackbine, and I'm the secretary of this fine organization. And I need to report that our September meeting notes are on our fresh October newsletter, just came out on October 1st. And we have some new and renew membership from September. Renewal is Paul and Nancy Roll and Brian Teamy. And then we had new Maria Bognar, Hadley Kleinschmidt, and here tonight, Ernest and Mill Mish. Forgive me if I got any of those names off. And that's what I have to report. All right, thank you. Thanks. All right, outreach, Jeff. What is going on?
So who would drive an hour and a half to see a telescope? Okay, I might have to apologize. Will you
want to bring that up?
share
Yep.
that
Yeah.
thing? My apologies if I miss anyone. So Astronomy at the Beach, I want to personally thank all the people who helped us out on behalf of the WASP. So Bob, Dale, Doug Bach, Ken Burton, Flash Photography, Mike O'Dowd, Tina Wong, Laura, you weren't there? Shame. Mark Kedzier, Greg Nizo, Riyadh up there. Think that's I want to say it's everyone. If I missed you, I apologize. I'm all over the place today. We made it happen. I think we did pretty good. Ford Club razzed us a little bit about our tablecloth, so it will not be repeated.
Okay. We've got this
table.
WASP banner that hangs down in front of our table, and the Ford guy says, "Hey, we last time we were here, we saw that. We really liked that. So we got something better." And he's like, "It's on. I want a back banner, a better table banner."
It's on. I might have a 55-inch television that we can bring to the next one. So if you need a big monitor, we'll make it happen. Yeah.
I would love that.
Okay. Then they'll have a 60, and then we'll have to get a 70.
Darn it.
So yeah, Astronomy at the Beach, I think, was a major success. I think Jonathan was the only person that complained that there was no beach. No one else really noticed. We flew under the radar. So, and then I have to apologize. I did a spaceship gig this weekend out in Adrian for the Planewave Open House, and I was so preoccupied with my own situation, I didn't actually tell the membership, "Hey guys, the Planewave Open House is this weekend. You should check it out." So you missed it. Sorry. You missed that. That is a 1-meter telescope that the event was from 12 to 6, but then you could hang out, and when the sun set, we actually got to look through a $600,000, 3,500-pound telescope. Pretty cool. Price per inch, it's really not there. I'll take the big Dob any day of the week. But can I?
Yeah.
How do I?
Mouse right here.
Oh,
Next.
yeah. So that's me. Click past that. We've all seen that. So this is a rotating dome that this is their first one that they've ever made, but they're going to start making more of these. This holds their 0.7-meter telescope, and this is going to a mountaintop in Chile. So if you're not familiar with Planewave, they are a very high-end telescope manufacturer that moved from California to Michigan in 2018. They're in Adrian, Michigan, so they're a little bit of a hike from us. But I talked to these guys for hours. Like, I don't even know what questions to ask, but apparently they're kind of the only ones that are making this scale of equipment. So, they're not making 4-meter telescopes, but if you have the money, you can buy this equipment. This is their 24-inch. They can actually mount 2 of these on this pier mount. And they actually have some of these where that mount can just exist outside, no dome, and you can just walk up with a smaller scope and just place it on there. That's what they do with what they call their L mounts. This thing is capable of slewing at 120 degrees per second. Extremely fast slew speeds. And they build absolutely everything in-house. So this is their big one. This is a meter. I want to point out that their fork mount, you see they've got the big wheel there and then the base and then all these truss tubes. It's a truss tube fork. It'll be in the 15-minute talk that I just scheduled. It's going to be on Planewave. I think this is a 20 or a 0.2 meter. I don't know. This was under their test bed. And this is the sun going down and me just taking a bunch of pictures. So this is one of their what they call their L mount series. That you can park a bunch of different scopes on these L mounts. When they were dragging it out, the scope wasn't on it, and there's a guy sitting in that mount like it's a chair. Hilarious. I didn't get a photo of it in time, but they were imaging with this scope all night while we were looking through the big one. And then I think the last one is just us out at dark. But really cool event. They had a bunch of stuff for kids and lectures and all kinds of stuff. It's definitely worth the drive. I will put it on your calendar for next year. It's worth the drive to go out there. And honestly, I'm like super pumped that this exists in Michigan. Like we have an up and coming like premier telescope manufacturer in our backyard. I think that's something to be pretty proud of. Other than that, I don't have any official stuff on the calendar. I'm giving my Apollo talk at the Seven Ponds Club Saturday the 26th. So if you missed it or want to see it again, then I'm going to miss the open house. But that's it for me. If you want to get involved in outreach, come at me.
The telescope here at Franklin.
Yep. Tell us,
Quite that large.
not that large. I think it's like, 1920, something like that. It's one of their older ones, but man, cool stuff. Yeah.
Put it in dome on the end that was.
Is it a 19?
It's a 1990. That's what I thought.
Okay, publications is not here. Our newsletter is up. And if you want to contact the board for any reason, we are board@warrenastro.org. So let's see, special interest group. All right, astronomy in the news. I'm going to start off with my exoplanet update. So if you don't know what how many of you have not heard the word exoplanet? So you all know what they are. Oh, one person. All right. Well, that's fine. Exoplanets are planets that are orbiting other stars or free floating throughout the galaxy, not attached to any stars. Are also called rogue planets. First one was discovered in 1995. Today the count is 5,765 confirmed, up 9 from last Cranbrook, and 7,236 candidates, up 19. That's thousands of planets around other stars. That's just amazing. The European Southern Observatory, the ESO, creates the largest IR image of the Milky Way. The team used the Vista infrared camera, VIRCAM, over 13 years to create a map collecting 500 terabytes of data. It's the largest observational project ever conducted using an ESO telescope. So that's kind of crazy. The website, you can't download the entire thing in one thing. You've got to, it's in sections. It's so big. I'd love to see that on a wall. So Europa Clipper was scheduled to launch on October 10th, but hurricanes and all. So Jupiter's Moon Europa, well, the missions the mission is defined as Jupiter's Moon Europa is considered one of the solar system's most promising, potentially habitable environments. After an approximately 1.8 billion mile journey, Europa Clipper will enter orbit around Jupiter in April 2030, where the spacecraft will conduct a detailed survey of Europa to determine whether the icy world could have conditions suitable for life. Europa Clipper is the largest spacecraft NASA has ever developed for a planetary mission. It carries a suite of 9 instruments along with a gravity experiment that will investigate an ocean beneath Europa's surface, which scientists believe contains twice as much liquid water as Earth's oceans. So that's pretty cool. And speaking of hurricanes, if you want to see what's going on the planet, you can go to NASA Eyes on the Earth. When you get home, just type NASA Eyes, and you'll find Eyes on the Earth. You can see the Earth that is right now, and there's like hurricanes everywhere. Kind of crazy. The predicted nova of T Corona Borealis is still due, and we're waiting. I've seen at least one article saying astronomers have lost hope. Yeah, well, we'll see. See if I can share this. I have this up. Where is it? There. Well, no, there's NASA Eyes. There's that thing that's going on. But I wanted to show you SDO.
Did anybody see the lunar eclipse? Yeah.
There it is. All right. Yeah, there it is. So I'll share that to Zoom. I brought this up. This is from NASA Solar Dynamics Observatory. There is the photosphere of the sun. And my reaction when I saw that was, oh my God. And I think the parrot was scared on my shoulder when I did that, because there's a lot of stuff there. And I pulled into the parking lot here, my phone buzzed. I looked down at it, and X1 point something flare. So another big one, like today, like right now. So yeah, the sun is angry.
If we have a roller for that, we're shooting what about 3 days?
Yeah, actually, I'll check spaceweather.com. I actually did not check space weather, but yeah, it's well, depending how big it was, usually 3 days. Yeah. So if you're on Facebook, check out Solar Activity. They're a really cool group, and they have amateurs posting just the most amazing pictures of the sun. So Riyadh, any double star stuff going? Well, you didn't have any they're cloudy at the last Stargate.
Yeah, unfortunately, we did not. However, next open house, we will be looking for more double stars and new ones, hopefully too.
Can Stargate resolve Polaris as a double?
Stargate should be able to go down to about 0.6 arcsecond, but that is going to depend on the night condition, scene conditions.
So the Polaris, I don't know how many of you know Polaris, the North Star, right? It's a double, and they orbit each other. I'll show you in Space Engine. It's really cool. They orbit each other like this. It's very cool, and it takes 100,000 years for them to orbit each other. And pardon me?
Comment.
Yes,
Polaris is a triple star.
it is a triple.
But the third star is so close to Polaris that only the Hubble telescope has so far been able to.
But I didn't know that. Wow, I'll have to check that out in Space Engine. I did not. I've shown a lot of audience that it's a double, but I have not even seen that one. It must be very close. So if anyone wants to start a special interest group like a double star group, or computers, or radio, or education, whatever, light pollution, go ahead and let us know about it. So observing reports. I know that Bob, do you want to come here and show your pictures?
Yep.
All right, I'm going to show some pictures by Bob Berta here.
I didn't take pictures of that.
There we go. So full screen that. There we go.
Shadow.
Get out of here.
Okay.
All right.
Okay, well, let's not show that one first. Let me,
Oh, okay.
how do you go back? Just. Yeah, that one there. Okay. Okay, if some of you remember, if you've gone to a meeting in the last couple of months, this is Sharpless 2-174, which is the nearest nebula to Polaris. It's very close to it. And actually, I did a write-up in the newsletter. Some of you may remember that when Sharpless discovered that, they thought it was a planetary nebula, and it's not. It's not really that. It's something else, just a nebula. But anyway, when I took this picture, that was with my 80mm refractor, and I said, that'd be a cool picture to get a long exposure. I bet there's some cool colors in that. So in fact, there is. How do I go back? Okay, this picture is about 40 hours.
Get out of the way.
This is about 40 hours to my six-inch Apple refractor, which I think that's pretty cool. Look at all the gas goes off from the sides and everything else. That has to be, I guess, my new favorite nebula I've seen or photographed ever. I think that's so cool. It's sort of an overlooked item because it's hard to see. It's very, very faint. And like I say, it's close to Polaris, so it's not too hard to find. Now let me go back to.
Yeah, that's cool. That's good stuff, man.
Go back. Okay, this is another. I took this picture 2 days ago. This is Sharpless 2-101 or NGC 6910. These are all up in Cepheus. And that star is, I think it's, I got it written down here. Yeah, it's Eta Cygni, that bright star in the middle. This is about a 3.5 degree wide field of view taken to my 8-inch hyperstar. So that's kind of a cool picture too. That was, again, this was taken from my backyard, which is in Macomb Township. With the new filters, the filters they have now with the narrowband filters, you can get through a lot of light pollution and everything else. It just astounds me. The pictures I can get now. I'll go back. And this is a picture I took 2 days ago. This is the sun. I did take some pictures that included the prominences on it, but unfortunately, the prominences that particular day were very small. So I didn't bother to include them, but I thought this is a cool picture. It has a lot of detail in that. If you go back, I also colorized it. This is the same thing, only colorized. When you're doing solar astrophotography, what you want to do is do it with a mono camera in black and white, because that way you get the most resolution, the highest, I guess, the wide range of values of the grayscale. And then once you finish your picture with all the tricks you do to it, then you colorize it, go into Photoshop. In this case, I made it yellow more or less, but if I want to make it purple, green, blue, I could. So just for aesthetics. Actually, I kind of like the black and white shot. That's kind of a raw thing. What you'll see there is the grain, you might say, on that. That is the plasma on the sun bubbling up. Where the gray area is, a gray color, that is sort of the middle heat range of what's on the sun, about, I think, about 5,500 degrees or so. Where you see darker, the blacks, those are about 1,500 degrees colder. And when you see the whites, those are about 1,500 degrees hotter. And that's all these are in Kelvin. The little filaments on there, which they are called filaments, those are the flares that come off the sun sideways. You've all seen the prominences or flares. When they come at you directly off the sun, it looks like a hair on the surface of the sun. That's because they're moving so quickly, it changes the range, or we call it the angstrom, slightly changes the angstrom as they come towards you. And also as they fan out, some of these, like this one over right where the hand is, the hand showing on there? Yeah, where the hand is, that's just an area that's kind of spreading out. If that same thing was on the side of the sun, oops, you would be seeing a prominence coming off the side of the sun. Widen out. And the black spots there, those are sunspots. So with a normal, just a high density filter, so you can look through a telescope, you can see these sunspots. But all this other stuff, you have to have an H-alpha telescope, and many of us have those. In fact, if you go to our various outreach events or open houses during the day, before we start looking at the night sky, when it's sunny out, we'll have these scopes out there so you can see that. So this is a really cool thing. I love solar astronomy. In fact, my old buddy, Marty, Astro Marty, He's the one that was really got me really heavy into nighttime astrophotography. And I've always done ever since I was a little kid. I'll be 77 the 20th of this month. I've been into astronomy ever since I was about 6 or 7 years old. And I started doing pictures probably when I was in high school using hypered film. Some of you old timers like myself remember about using hypered film. But things have come a long ways. And the thing is amazing to me that despite all the light pollution and everything else, you can get into a pretty light polluted area like where I live in Macomb Township. You can take pictures, get pictures like some of these pictures here. It just boggles my mind. Okay.
All right.
That's it, I think. Sorry, I think
Yep.
that's it, I think.
Yep.
Here we go.
All right.
Okay. Thank you.
Right.
The site right now is extremely active. We have, this is actually a picture when you get a chance, we have a great comment, so you're the site is actually in.
Oh, we've got one of those?
Yep. And there is an extraordinarily great.
Right. Was anyone at the Great Lakes Stargaze? You want to talk about it really quick?
Am I the only one?
We had two. We had three people. How was it?
It was good. I mean, it was, I wasn't there the last day because it was supposed to rain, Saturday night. But, Thursday and Friday, the scene was pretty good.
Awesome.
Friday was much more stable. The turnout was excellent. Not as good as probably like 20 years ago when it was really hopping, but it's consistent with what we've seen in the last 5 to 10 years. It was beautiful. The weather was beautiful. I saw a lot of people for 2-3 years. I know the bottom feeders were all down at the lower section and cooking away, and Doug Bach was part of that. So it was a great time. I highly recommend everyone go if they can get a chance to break away. Honestly, it's one of the best areas to just enjoy astronomy, meet other people. And then, during the day, there are things to do. It's a beautiful area, and the Amish come and bring their baked goods. So it's a wonderful experience.
Yeah, Great Lakes Stargaze takes place in Gladwin.
Gladwin.
Yeah, Gladwin.
I've heard though, I just got a phone call to a friend of mine who's there. And it won't be there next year.
No, they're changing the date.
Right, well, they're changing the date.
They have to change the date because they announced that they're using that particular date of new moon for another event.
Yeah.
So they have to shift it by a week. That's what I heard. Well, at least that's what they had announced right before.
They were worried about that.
Yeah.
Yeah. Good.
I had a quick observing report, or
Go ahead.
actually an outreach report and an observing
You want to
report.
come up here and do it?
I'm sure. Why?
So our watching audience can see it.
Sorry, I have a cold, not COVID, but I don't want anyone else to get my cold. So on the second day of astronomy at the beach, we weren't able to make it out there because that was our block party in Dearborn. But we did set up our Coronado Solar Telescope, RIP, and we got to show all of our neighbors a very similar sun to the one that Bob was showing you, with prominences and filaments all over the place and a couple of good sunspots. And as usual, everyone was really excited to see it. And then on our own, I don't know if anyone else has joined the Michigan Aurora Chasers group that we heard about at Astronomy at the Beach. Has anyone, if you're on Facebook, it's probably the least stressful thing that you're going to find on Facebook this time of year. But that said, it's not stress-free. So this last weekend, I don't know if anyone else is watching the Aurora predictions, but it was a very stressful weekend. The auroras were supposed to come in on Friday night, nothing. They're supposed to come in on Saturday night, nothing. They were supposed to come in on Sunday night, and they did come, but it was like an hour from 9:45 to 10:45 p.m. when Diane and I were on the road. And then again at like 3 in the morning when I was fast asleep. So But even though we didn't see any auroras this weekend, we saw some nice meteors. Did anyone see the fireball that went over Macomb and Oakland County? So that was super cool. It was a really significant fireball.
Darn it.
And Diane and I got to observe not just our old friend, the Silver Coin Galaxy, down in Hydra? The Sculptor Galaxy, yeah. And but we also got to chase a number of globular clusters around there. So there's a couple of Messier objects down there, M75 and M60. One of the globular clusters in the 60s, and a whole bunch of interesting NGC globular clusters and galaxies, including some very ghostly ones. So this is the only time of year to really see that stuff. So if you can get a good south view, you should go look at Sculptor. Jeff.
Should we be looking for rocks?
Rocks. I do not know what the blast, like what the whatever that field is called, strewn field would be, but it came down over Michigan somewhere for sure. I haven't seen, but it's on, if you go look at like Meteor, New Baltimore Meteor, sorry, Bob, 2024, there's a bunch of videos and stuff. So I don't know. It might be in your backyard. Go look.
Of all people, why have I not heard of this?
Exoplanets.
Yeah, well, I like exoplanets. All right, so Dale, you ready for a show talk?
On that computer.
Yeah. Mouse. That. Oh, awesome. I don't have to look it up then.
Let's get it up.
No, I don't want LibreOffice.
I'll hold it.
You're right. With PowerPoint, because I got PowerPoint now. So there, all right, now I got to.
Hold the screen. Got it. So can I just use the down arrow key to advance?
I think so.
I
Yep.
Yeah.
Yeah, there.
Good.
Right. Internet folks, are you seeing the presenter view or the
We're seeing presenter view.
don't want you to see presenter view. All right, hold on. There it is. Right? All right. Okay. Check is done. All right. Nope, I have some glasses. All right. I'm going to be introducing Dale, but he usually introduces, but it'd be a little weird for him to introduce himself here. So Dale is member of the WASP since 1998. Oh my goodness. Served as an officer in the WASP many times. He has a doctorate from Carnegie Mellon University and has worked as an industrial physicist in the automotive industry for 32 years. He now teaches astronomy at Macomb Community College. His topic tonight is measuring latitude at age 14. Take it away, Dale.
Thank you. Thank you, Bob, for that excellent introduction that I wrote. I handed it to him just as I walked up here. Okay. At age 14, I didn't know anybody that was into astronomy. No astronomical equipment of any kind. no mentoring. But I was reading some book, I don't know what book it was, and they showed a simple diagram showing how you could find your latitude by making a measurement of the North Star. And I thought that was kind of neat, so I decided to try to do that. Guess what, Bob? The slide's not advancing when I.
I'll send it to them.
Oh, is that how you? Ah,
There we go.
okay, thank you. So, just, I mean, I want this to be simple for everybody here. So I don't want to assume everybody knows what latitude is. So does this work? Let me see.
Yeah.
So you can see the cursor.
Oh.
No, it's over there. It's actually. Can I turn the laser on? There you go.
Ooh,
See that? There
nifty.
you go.
Woo. Computers are not my strong suit. Yeah. Okay, so over here is how you define latitude. Here's the spin axis of the Earth. Here's the equator. 0 degrees latitude at the equator. You come up this way to the North Pole. It's plus 90 degrees latitude or 90 degrees north. Go down this way, it's down to minus 90 degrees latitude or 90 degrees south. So where we are and where Toledo, Ohio is, where I was, is somewhere up in this region. So I wanted to find out my latitude, how many degrees north of the equator I was. There's also longitude, which measures where you are on the Earth in the east-west direction. It's sort of arbitrary. I mean, for latitude, the equator is 0 degrees latitude, no ifs, ands, or buts. But for longitude, you can define 0 degrees longitude to be wherever on the Earth you want it to be. So some British astronomers way back who had a telescope in Greenwich, England, said, we are 0 degrees longitude. And Great Britain was a great seafaring nation then. They needed accurate longitude and latitude measurements, so that became the world standard. But I'm just going to be talking about measuring latitude tonight. So I don't know what book I saw that diagram in, but I'm sure the diagram looks something like what you see here. I hope. So I'm going to explain this diagram a little bit, but in essence, this angle A is going to be my latitude, and it will turn out, as I will explain, that if you can measure the angle from the North Star to the horizon, that is also A, your latitude. Let me walk you through that a little bit. I know for people that are into geometry, it's like you get it right away. I hadn't taken geometry back then. So here I am at position P, this angle A from the equator to where I am, that angle is my latitude that I want to measure. And if you have two parallel lines and a straight line crosses them, then this angle that I call angle B and this angle is the same angle. Okay, I think that's pretty obvious. So here's one of those straight lines pointing at the North Star. And where I am, if I point at the North Star, I'm pointing in the same direction in the sky. Those are parallel lines because stars are so incredibly far away, just boggling the mind far away, that those lines are effectively parallel. So here's a straight line crossing through these two parallel lines. This angle B and this angle B are the same angle. Then the angle between the equator and the spin axis of the Earth is angle B. And angle A plus angle B is this right angle, 90 degrees. So there it is, angle A plus angle B equals 90 degrees. Here's another 90-degree angle, also known as a right angle. So angle A plus angle B is 90 degrees. So since B here and B here are the same, A here and A here have to be the same. So again, if I can measure that angle A, that is my latitude. Then I had to know, where is the North Star? Okay. I didn't know anybody that was into astronomy at all. But I had been in the Boy Scouts, and we camped out somewhere one night, and I think it was the scoutmaster knew how to find the North Star. So he took us out where we were in a dark area, and he explained something I'm sure 90% of you know, how to find the North Star. If you can find this, it's the Big Dipper. It's part of a constellation called Ursa Major, Big Bear. These are called the pointer stars. They approximately point toward Polaris, the North Star. You go about 4 or 5 times the distance between them, and there it is at the end of the handle of the Little Dipper, which is part of Ursa Minor, the Little Bear. So I remembered that from the Boy Scouts. That's how I knew how to find the North Star. I mean, it's not like super simple things. We don't know anybody hardly that knows anything about any of this stuff. A little bit goes a long way. So this is a picture of the picnic table with one of my brothers sitting on it, that I used as part of my apparatus to measure the North Star. My father did some carpentry, so he had a bubble level. I used that to level the picnic table in both directions by putting shims under it till I got it level. And my mother, when she would do laundry, she would hang the clothes out on a clothesline, and we had wooden clothesline props to hold the line up. This is not from our backyard. This is just a picture I found on the internet that shows what she did. And I borrowed one of her clothesline props. She had, I think, 3 of them, and I picked the one that was the straightest. Okay. So then here's my apparatus. Here's the picnic table with a bubble level. Here's the clothesline prop, which I had one end sitting on the ground, and I moved it back and forth until this pointed accurately at the North Star. I then had a piece of cardboard from the back of a tablet, and when I was lined up on the North Star, I drew a line along the wooden prop.
What did you do? Stick your eyeball right down by the ground and look up the rod?
As best I could. I mean, this is crude, but it's all I had, you know? It's all I had. So I don't know where I got a protractor, but I found a protractor somehow. Maybe I had to go buy it. I don't know. can't remember. And I measured on a piece of cardboard that angle A as accurately as I could, estimating to a fraction of a degree. I got 41.2 degrees. Okay. I think up here we're what, 42 and a fraction of a degree, something like that. Where I was in Toledo is 41.2, but that was what I measured. Then the question was, what is the right answer? Okay, well, how am I going to find out? Now you can just pull out your cell phone and, what's my latitude? Boom, you got it, right? None of that was happening back then. So I went to the library. It was within walking distance of my house. And I had a collection of maps. I found various maps of Ohio. Most of them didn't show latitude, but I finally found a map that did. This is just a map of Ohio I pulled off the internet, and I figured out where to put lines for the latitude. Then the problem was Toledo was not right on one of those 1 degree lines. So I had to figure out, how do I figure out what fraction of a degree it is to get to this point? So I had to figure out how to interpolate, which I had not got to in school yet. But I was able to interpolate and get my latitude to within 1/10 of a degree. So from the map, I got 41.7 degrees, my data 41.2, 0.5 degrees error. I was quite happy about that. I'm sure my errors, this was luck that I came out this close. You're correct. Trying to sight along a wooden piece of wood at a star is, and Polaris is not exactly on the spin axis of the Earth. It's off by, today it's off by about, I think, 0.7 degrees. Trying to measure that angle with a protractor has error in it. So all I can say is I was very happy. I hope everybody could follow all of this. Sort of almost a humble or embarrassingly simple thing. But back then, for me, it was a challenge, and I enjoyed my first astronomy thing, So thank you. Yes, Jeff.
Gonna follow it up with more observations.
Yeah.
Can we get down to 1/100th of a degree?
Well, yes, 100th of a degree would probably be a challenge, but certainly to 1/10 of a degree. I did do some related measurements a few years ago, out of which came latitude and longitude, by doing measurements on the sun instead of the North Star, where I measured the angle of the sun by using the shadow of a stick, the way the ancients did it. And out of that data, I got latitude at least to 1/10 of a degree. I think better than 1/10 of a degree. And you can also get longitude out of that. And you can get the tilt of the Earth. It's like 23.5 degrees or so. You can get all kind of stuff out of this. It's amazing what you can get out of that. But yeah, yes.
You mentioned getting a longitude. You would need a time for that.
Yes. But to get longitude, you have to know accurately what time it is. Yeah, here in this area, what you measure when the shadow of the stick is the shortest distance, that is true local noon. And here in the summer, that occurs around 1:30 in the afternoon because we're on daylight savings time and we're over toward the western side of the Eastern time zone. But when you measure true local noon and compare it to the time in Greenwich, okay, that'll give you your latitude. I'm sorry, your longitude. Any other comments or questions? Again, kind of a simple thing, but it was fun doing it. Thank you.
Alrighty, so it is time for the snack break, and look at that, we are right on time. Amazing. So we are going to reconvene at 8:25 for our feature talk, and go grab a munchie, grab a bio break, and meet back in 20 minutes or so. Ready? There. We got a chat message here. Applause. There we go. Okay. I wanted to bring you this up. Running that.
Carl Mary, who's gonna give yeah, yeah, you did this here. Yeah.
Is Carl Mary still here? Is Carl or Mary still here? Okay.
Wow, that thing is angry.
Yes. The question about some of the talk on radio astronomy, like that, he's the guy, we should have him come in and give a talk. He's in the ultra astronomy talk.
Really?
But he's an expert on radio telescope.
Awesome.
And he'll come in, he's got some fabulous talks.
I would
There's a
love
couple
to.
of guys
That's
know
awesome.
So you can give him a call, tell him listen to Greg Hagen, and or you can write to him too. Just write down his number or whatever.
Actually, no, we can't. And here.
Yes, TL Hagen. People.
I was gonna share that with me.
Oh, sure.
Yeah, share.
Share.
V card file. Messages. There's messages. Messages. Yeah, me in there, Bob.
Yeah. He's probably on screw up.
Here's my number.
Yeah.
586.
Here.
Yeah. 764. There I am.
It's up there.
I wanted to show you something.
Like that.
So what?
And
Don't know. I do it.
might have to go over. Well, I might have to go to
Yeah, when you get a minute, I'll show
yeah,
you.
might have to go to this. There, and I may have to there, see what's see up there.
There it is. Got it.
Yeah, okay, got it. Okay, good.
Awesome.
Yeah.
Thank you.
He's got fabulous lines on radio astronomy.
This is right now on the sun,
Yeah.
and there's the comet.
Yeah.
But that,
Oh, that's cool.
yeah, it is good.
Anyway. Tell what you're looking for and tell him and recommend him. He ought to come in, have him do a whole presentation. 'Cause he's fabulous talks about radio astronomy and how they work. He was one of the main drivers of the out at McMath Holbrook, the radio astronomy group out there. He is one of the main guys. He brings in portable radio stuff and everything. We go out and give talks at schools and everything. People that demonstration. Pretty cool. Yep. There's no problem. Anyway.
Anyway, thank you for the contact.
Survival, not right now, but the.
Wow, there are a lot of people here.
Buy some seeds, if you want to have a fundraiser.
Yep. Got that going. All right, if you everyone take your seats, please. Time for our feature presentation. Hey, Jonathan. Got the mouse. I got the laser pointer, so the laser pointer works up there, and you can use that for the slide forward and back here.
What laser pointer?
That laser.
Oh, I see.
If you're gonna laser.
I can.
Should we start? Okay, everyone, if you could take your seats. We need to get going. Have a seat, everyone. I've been reminded to announce that the Michigan Mineralogical Society, which meets here 1 week later than us typically, and many other mineral clubs and gem clubs, are having their annual mineral and gem show at Macomb Community College this coming weekend, Friday, Saturday, Sunday. Macomb Community College, South Campus at their expo center there. It's a huge, a huge event. Lots of fun. Take a few dollars, you can buy all kinds of stuff. So just if you didn't know about it, you can also Google it and find out information about it.
Before you start, calendars are available here. You can pick them up and purchase them. And banquet tickets, you can buy those tonight. $35 now, $40 at the door. I'll be sending a mailing out about the banquet. There we go.
Okay, thank you.
Calendar
Yeah.
right there.
We publish a calendar every year. Each month, there's a picture taken by somebody in this organization. Open it up and show them. Yeah, all kind of really neat pictures taken by us. How much are they?
20.
$20. So you can buy them tonight. And as you heard, our annual banquet is coming up in December. You can buy tickets here tonight for $35, $40 at the door. Okay, this next presentation is going to be a bit of a contrast with the one you just.
You are not going to be replicating any experiments at home.
That's right. The one I gave was sort of the lowbrow presentation.
I take that back. Actually, there is one that you have already done, whether you know it or not.
So this is going to be ratcheting up the IQ level a little bit. So Jonathan Kade has been a member of this August body since 2007. He has served in various roles as officers in this club, including being president. And his wife has also been president, I might add. It sort of runs in the family, I guess. And he says he's interested in everything. So this is just a subset of his wide-ranging interests. He enjoys sharing the astronomical aspect of his interests with fellow aficionados. And he thinks the scientific establishment is generally pretty excellent at what they do. We're going to find out what he has to say about alternatives to the Big Bang tonight. Jonathan.
So first off, I did want to dedicate this presentation to Marty Coons. We missed the eulogy for Marty that was given earlier by his friend Carl. But Marty is the person who brought me and Diane into the club. He's the guy who, before we even joined the club, we got to know about the club through Mike Narlock. So we've been attending WAS events since 2003. And oops. So if in a different continuity, Marty would probably be giving his Dark Universe talk tonight, his very frequent talk about ways that space can kill you. So we are very sorry that Marty's not giving that, and maybe you will be by the end of this presentation. But by the time, but I did want to also give Diane an opportunity to share some of her thoughts about Marty too. She actually co-hosted Space Pirate Radio with him for almost 15 years. And so she had a weekly radio show with him, and at one point twice weekly. And so she knew him and worked closer with him than most people in the club. So I did want to give her a couple of minutes for that.
Thank you, Jonathan. Where's the camera? There we go. Thank you. So, yes, as Jonathan said, I worked closely with Marty for almost 15 years. He wore a lot of hats. He was Solar Marty. He was Stargate Marty. But to me, he was Captain Marte, as he always pronounced it, the captain of the ship Argo Navis, which was our fictional space salvaging pirate ship that we sailed the seas of internet radio on a weekly basis, accompanied by our intrepid engineers and crew, including Dale Teamy here as one of our crew members. And we had a rollicking time of it. It wasn't all just fun and games, though. Science outreach mattered very much to Marty, and the radio was one of his vehicles for getting the message across about the importance of science, of rigor, of logic, of respecting the universe. And he delighted, though, in October, because that was when he would do his smorgasbord of ways that space puts an end to humans. And I will think of him every October. It's a part of my life that I deeply miss. Even now it seems strange for 9 o'clock on a Wednesday to roll around and there's nowhere to log on and Marty's not there. But hopefully the internet ripples that he and I did together will be out there influencing people, and the connections that we made will endure. So Marty, miss you every week, man, and hope wherever you are, smooth sailing and clear skies.
All right, so now let's get to the boring part. So I do have a word of warning. If you are here to observe a discussion of the adventures of young Sheldon, this is not going to be the time for you. This is not the television show. So we are going to be talking about the real Big Bang Theory. We're going to talk about what it is and, importantly, what it isn't, because a lot of the things that people raise as objections to it tends to be the stuff that isn't part of it. We're going to talk about some of the things that it has predicted and whether or not we've observed them. We're going to talk about the problems with the Big Bang cosmology. We're going to talk about the alternatives that have been proposed and actually some of the visions of the universe that preceded it and that are still with us today. And the constant focus is how can we test stuff and how can we, what experiments can we do to feel confident that we know what's going on, at least to a certain extent. So the Big Bang, as we know it, dates back to 1931. It was proposed by a Belgian Catholic priest, Georges Lemaitre. He called it the primeval atom hypothesis, or the cosmic egg. And in the original paper announcing it in, I think, 1935, which was published in an obscure Belgian astrophysical journal, he derived Hubble's law from the observations that people had made of supernovas and other galaxies 2 years before Hubble published his paper. Unfortunately, Lemaitre translated his own paper for the wide publication of it, and for some reason he left that part out. So it's in Europe they call it the Hubble-Lemaitre law, but in the US we just call it Hubble's law. But Lemaitre got there first. Lemaitre was not just a priest. He was also a World War I soldier. He was a musician. He was a physicist, and he was completely blown away by Einstein's theory of relativity. Worked closely with many other physicists of the time, from Arthur Eddington to Alexander Friedman. And he wasn't the first person to sort of realize that sort of impact that general relativity and the observations that were coming out of the grand observatories starting to be built across the world would have on our view of the cosmos. Alexander Friedman in 1922 published a paper basically saying the universe is expanding, didn't know what the rate was, didn't have any explanation of sort of the causes for it. But Friedman unfortunately died at a very young age in 1925, shortly after publishing the paper. But the metric, the actual set of mathematical equations that defines what the Big Bang is called the FLRW metric, the Friedman-Lemaitre, Robertson-Walker metric. And we'll show that in a second. So what you need to know about the Big Bang, probably most of the people here know, there's no bang. It's not an explosion of any kind. What it is, the expansion of space-time. Like before the Big Bang, there isn't space, there isn't time, which is a concept that kind of breaks our brains. And importantly, it doesn't answer at all. It doesn't even try to answer what happened before the Big Bang. What we try to do with the Big Bang is we try to explain the stuff that we see in the universe that we live in. The point of it is to be able to make predictions about how our universe developed, how galaxies relate to each other, how subatomic particles relate to each other, how the fundamental forces of the universe work and whether they change over time. It doesn't have anything to do with multiverses. It doesn't have anything to do with whatever happened before the Big Bang. It's just really a model of what the universe acts like, and if we go back in time, what the universe acted like more earlier in our existence. In engineering, and at least in computer science, there's a common saying that all models are wrong, but some models are useful. And the Big Bang is definitely one of those models. So this is the one and only equation that you're going to see in this talk, but this is the FLRW metric. I am not going to dive into it, but this is what all the fuss is about. Underneath that, you see a sort of a depiction of what has happened after the Big Bang, and we'll be looking at that in a number of different ways. But what this is intended to show is, I guess I can use the screen thing here. The reason this is an exciting time for this topic is that Hubble was able to see to sort of this era of galaxies after the Big Bang. The Webb is able to see way, way further back. And we've already heard some exciting stuff as a result. So this is sort of the horizontal view of that. And so on the left here is the Big Bang. It's the so-called singularity. What goes before that? Nothing that we're going to be talking about today. Everything before that is in the realm of religion or metaphysics or pure mathematics. It's nothing that we can observe, unfortunately. So, I mean, yes, in a space-time sense, we exist in a four-dimensional reality, right? We have the three dimensions of space, and then we have the dimension that we don't see and can only move in one direction in time. But the Big Bang includes time, so there isn't really a before, but that's an unsatisfying conclusion to a lot of people. And yet, we're still not going to talk about it. We will talk about why we can't talk about it, I guess. Is essentially yes. So this is kind of the graphical depiction of the process of the Big Bang. And now we're going to talk about kind of how it breaks down into pieces. So the very, very early universe lasts from basically 10 to the minus 43rd second after the Big Bang to about 1 second after the Big Bang. The formation of particles and nuclei lasts from 10 minutes to 380,000 years after the Big Bang. Sort of the dark ages and when fundamental atoms form is from 380,000 years after the Big Bang to 100 to 150 million years after the Big Bang. And everything else is the universe that we know of. So with the Webb telescope, we can see back to essentially the entirety of the universe as we know it. And that's super exciting. So in the beginning, and I should say, the sort of religious overtones of this were one of the major reasons that the Big Bang got a lot of pushback early on. The fact that a Belgian Catholic priest was proposing something that sounded to a lot of physicists at the time, a lot like creationism, was definitely behind a good large portion of the pushback. And it is kind of ironic today that it seems like a lot of the problems people have with the Big Bang seems to come more from religious people, which confuses me, but be that as it may. So at the very early instant after the Big Bang, 10 to the minus 43rd seconds. So, you have no sort of sense of what small time scale that is. It's, the lowest that a human can reasonably detect is like really milliseconds. Maybe certain people can detect certain things at the microsecond level. That's 10 to the minus fifth. It's not, this is not something that we can experience in our everyday lives. But in the singularity, before anything starts sort of happening, the temperature is 1.4 times 10 to the 32nd Kelvin, way above anything that exists in our universe today. The hottest part of the sun is in millions of Kelvin, and that's 10 to the 6th power. So this is 10 to the 32nd power. The density is 5 times 10 to the 96, almost a Google kilograms per meter squared. The densest stuff that we know about, basically black holes or neutron stars are not as dense as that. And the standard model of physics says that at this early stage, all of the fundamental forces, which are gravity, the thing that holds planets to stars and stars in galaxies, a strong nuclear force, the force that binds the nuclei of atoms together, the weak nuclear force, the thing that holds electrons in orbit around the nuclei of atoms, and electromagnetism, which is light, electricity, infrared radiation. All of those in the very early singularity are one unified force. That's what Einstein spent the rest of his career essentially after sort of standardizing the general law of relativity, trying to theoretically prove, and was never able to sort of make it work. So we're here in the quantum gravity era. And then the first thing that happens after that sort of singularity is that gravity breaks away. So gravity is the first thing that separates from everything else. If you look at this graph, so here's gravity here, then the strong nuclear force, the electroweak force stays unified relatively late, and then weak and electromagnetic separate. So already, if you look at those temperatures, already in the first, from 10 to the minus 43rd to 10 to the minus 36 second, that's 7 orders of magnitude. The temperature has dropped by 10 to the 6th orders of 6 orders of magnitude. So it's cooled down tremendously in that expansion, or what we will talk about later. Okay, so now we are in sort of this band here where gravity has separated out. See this inflationary epoch here? We'll be talking about that later. That's not part of the standard model of the Big Bang, but it is part of the standard model of the universe now. So the next couple stages are really important for particle physics. And if you are not familiar with particle physics, don't worry about it. But just to give you kind of a reminder of what the various words are. So bosons include things like photons that transmit light, the Higgs boson that gives particles mass. And so bosons are, we can detect them experimentally in the lab. When we detected the Higgs boson about 15 years ago, that was huge news. Fermions are sort of the matter that we're familiar with. So that's baryons, protons, and neutrons, and their antiparticles, and then leptons, electrons, and neutrinos, and their antiparticles. So those words will come up, but just leptons are electrons and neutrinos, baryons are protons and neutrons, bosons are photons and other stuff. Basically, the bosons, the so-called gauge bosons, are the things that make physical forces work. They're sort of the carriers for the strong nuclear force, the weak nuclear force. The photon is the carrier for electromagnetic force. The Higgs boson is the carrier for gravity. There's also a proposed graviton that's never been detected. And so this is sort of how they relate to each other. So we have the quarks that assemble the other pieces here, the leptons here, and the gauge bosons. So then we are in the electroweak epoch. So that lasts for a staggering 10 to the minus 36 to 10 to the minus 12. We're starting to approach the range of time scales that we understand. So the strong nuclear force separates, it becomes a force. And when we say separate, what it means is that it kind of takes effect. Earlier, there's nothing to carry the strong nuclear force. And so until the W and Z bosons form, there's no way for that force to do anything. The temperature is now cooled to 10 to the 22nd Kelvin. So here we're right here after the inflationary epoch. And then we go into the quark epoch. Wait, wrong quark. So at the quark epoch from 10 to the minus 12 to 10 to the minus 6, which again, like this is starting to get into the realm. You probably can like at least here, your hearing goes down to 10 to the minus 6 seconds, probably. So the electromagnetic and weak nuclear force separate, and now we have the four fundamental forces that we know and love today. The Higgs mechanism turns on, and particles can be massive. And then a plasma of quark and gluon stuff fills the universe. And this is going to be a repeating pattern. So basically, there should be roughly equivalent quantities of quarks and antiquarks. There should be approximately equivalent quantities of both particles and their antiparticles. And then they should annihilate at the end, where 1 in a billion survive. And that's going to be a recurring theme. And at this point, leptons have formed. So there are electrons, there are neutrinos, but they also can't do anything. So now we're here. We're basically where we starting to look like the physics we know. And then things happen fast. So from 10 to the minus 6 to the first 10 seconds, the hadron epoch. So protons and antiprotons form, neutrons and antineutrons form. And again, they annihilate at the end, and we're left with the residue. The lepton epoch, the same thing from 1 to 10 seconds. Leptons continue to form at the majority of mass. Electrons and positrons annihilate at the end, and we're left with the residue. And then we're left with a universe that is dominated by photons, so electromagnetic radiation. And so that is where we are here. So from there, so you can think of this as so time is moving forward, space is expanding, and as there's more space, this stuff can actually start to operate, right? If there's no space, then gravity doesn't really work. If there's no space, then it doesn't make sense for electromagnetic radiation can't travel anywhere. So now that we have space for stuff to start happening, the protons and neutrons that are left over start combining into either a proton becomes a hydrogen nucleus, or a proton and electron combine into a helium nucleus. And that takes about 17 minutes. And then for 240,000 years, more or less, we just have a very hot, dense, opaque plasma soup everywhere. And it's so dense. And actually, I'm wearing a shirt to demonstrate it. So basically, it's like a grid of all of this plasma. And you'll see if you talk to me after the thing, there's all of the photons are kind of stuck in this matrix, and they're not actually able to go anywhere. So it's completely dark. It's very hot, but you can't see anything. So recombination starts happening. And throughout the universe, it's about the same temperature as the surface of the sun. And the pressure waves through this dense fog later on become, set up the structures of galaxy formation and the large scale structure that we see in our galaxy today. And at the end, when it's expanded enough that there's room for photons to travel, the universe becomes transparent to radiation. And so a photon that starts flying in a direction can actually start moving in that direction. Now, there's one problem. There's no stars yet. So there are no photons flying around at present, but that will come. Now, does anyone know? So we're actually into the physics that we see on an everyday basis here. Does anybody know where in our solar system photons are getting trapped in a dense matrix of super hot particles? What was that, Laura? Not dark matter. Dale Parton knows, but I don't want to call on him.
Or the sun.
And the sun, who said the sun? So a photon that, ends up on your retina from the sun today didn't just get created by the sun. That photon more likely than not spent probably 10,000 years bouncing around inside the sun before it finally made it to the surface and finally made that long 8-minute journey to get to Earth and hit your eye. So this is like, now we're into the stuff that we actually see in real life. So that's pretty fun. So this is kind of an depiction of the large scale structure of our universe. This is a computer simulation, but it's based on sort of our observation of galaxy clusters. So basically you can think of the large scale structure of the universe between, like, these are essentially galaxy superclusters. And if you look throughout, if you look at our local group of galaxies, right? It's a cluster of galaxies. They're all kind of gravitationally bound to each other, and they actually form sort of filaments through space. If you look into like Virgo, I'm sorry, I keep popping the microphone, but if you look into Virgo, there's the so-called Virgo supercluster, and that's like, one of these dense areas of the large scale structure. And so that comes out of the sort of inhomogeneity of the fog. And so the next one, I alluded before I started speaking to an experiment you can do at home, or at least you used to be able to do at home. Very few of us are able to do it at home today. So has anybody seen this in real life? Does anyone know what this is? Jim Shadowski.
Cosmic microwave background radiation.
Correct. So this is the so-called CMBR, cosmic microwave background radiation. Has anyone seen this with their own eyes? Bob Tremblay has, Dale Teamy has, Bob Berta has, Diane has, Kat has. I said Dale Teamy. So where would you have seen this with your own two eyes? I can guarantee that at least 90% of the people here. Yes, sir.
TV set.
So if you have ever used a cathode ray television and have ever had it tuned to a channel where there was no broadcast, if you saw that black and white static, a significant portion of that static was actually this. So that random noise that you were seeing was part of the cosmic microwave background radiation. And because analog television, like those, it's really translating radiation into a picture. In a real sense, you really were kind of seeing that firsthand in a way that if you use a digital set today, I don't think you can even get simulated static, but it's not the same. So if you can find a CRT, spend a little time looking at the CMBR, is what I'm saying. So this is like a view of the fog. This is like the edge of the fog. And no matter where in the universe you look, you see this fog. No matter where in the universe you go, you see something like this. It might not look exactly the same. But this is like the horizon of the visible universe. So from around 100 to 150 million years after the Big Bang, everything that we are familiar with today happens. Stars form out of this gas cloud. Galaxies, galaxy clusters, and superclusters form. The early supernovas in these early galaxies create heavier elements. Like the heaviest things created in the Big Bang the heaviest thing created in the Big Bang would be lithium, and not very much of that, mostly hydrogen and helium. And generally the universe looks like we see it. So part of what is called the standard model of the universe today is the so-called lambda CDM. And so that's dark energy and dark matter. So those aren't part of the original formulation of the Big Bang, but they are actually really what they are is a description of stuff we see. Dark energy is something that exists in Einstein's original equations. Does anyone know what it is in Einstein's original general relativity equations? I think I saw a hand, but it was what he called his biggest blunder. There was a factor, basically a fudge factor that he put in there called the cosmological constant. And he put that in there to make the equations work for what we were observing at that time. And he was like, I hate this. This is terrible. Why am I having to put in this fudge factor? And that dark energy, that is what we call dark energy today. So the question is not necessarily, you know, does it exist? The thing is that that kind of describes the fact that we see the universe expand. Dark matter is another thing that we observe in real life. We don't really know what it is. I'll be talking about some possible alternatives to the idea that there's some kind of massive particles that we can't see. But does anyone know offhand where we see dark matter actually take action in the universe today?
Every galaxy.
So every galaxy, especially spiral galaxies. So, when you see a cloud move in the sky, different parts of the cloud move at different speeds, right? If you stir up a pot with a mixture of stuff in it, different parts of the pot spin at different speeds. That's not how galaxies spin. Galaxies spin like a solid object. So the rotational speed at the center of a galaxy is the same as the rotational speed at the edge of that galaxy, even though the actual speed, like the actual linear speed of the particles near the center of the galaxy, the stars at the center of the galaxy, is much slower than the stars at the edge of the galaxy. So basically, you can think of spiral galaxies in particular as being like record albums spinning on a record player. Sorry, I'm increasingly old. So dark matter is really, what dark matter is it describes that behavior that we see in real life. So we'll talk about some possible alternatives to that, but that's part of what we call the standard model today. So what kind of things, what kind of things does the Big Bang model predict? It predicts that the universe is expanding, that there are galaxy clusters that are gravitationally bound where the galaxies in them stay together, but those clusters are moving away from each other. It predicts Hubble's law that stuff that is further out is moving away faster than stuff that is closer. It predicts that there will be a cosmic microwave background radiation. It predicts the relative abundances, like how much there is of helium and hydrogen in the universe. It predicts the cosmic neutrino background that we have proven with the neutrino observatories that are deep in the Earth. And it predicts the sort of large-scale structure we see in the universe. So here's the view again. So now, what kind of problems does the Big Bang have, and what should we be looking to solve? Well, one of the first sets of problems we have are a set of issues that are hopefully solved by something called inflation. If you remember back on those slides, we talked about the inflationary epoch. Those are the flatness problem, the horizon problem, the monopole problem. But inflation itself has some challenges. There is the baryon asymmetry problem. If you remember what baryons are, we'll talk about it again. There is a hypothetical problem called redshift quantization. Doesn't seem to really exist. There's the question of, are fundamental constants actually constant? And we'll talk about that. And you may have heard Dale Parton talk about this at the News and Review last year, but did the James Webb Space Telescope just double the age of the universe. Um, so in the very early universe, I'm going to talk about, I probably should have reordered these, but we have a universe that appears to be extremely flat. And what that means is like, I'll show a picture, but basically, if you draw two parallel lines infinitely long through our universe, those lines appear to never get closer and unite, and they never appear to diverge and separate. So we say that the universe that we live in seems to be very flat, approximately a curvature of 1, which is as flat as it gets. So I'm going to indulge in a little dark space there for a second when we get back to this. It solves the horizon problem, which is how come when we look at the cosmic background radiation across the entire sky, why does the temperature differ only by 0.01% across that whole expanse of the CMBR? It seems like that could violate the speed of light. Like basically it would have to, information about the temperature would have to travel faster than the speed of light for that to be true. And that's another thing that inflation tries to solve. And finally, the monopole problem without inflation, when you have particles kind of popping into existence, essentially the equations say that we should have a bunch of isolated North Pole sort of particles and isolated South Pole particles that don't have magnetic field lines connecting. So that's what a monopole is. It's just an isolated North Pole or an isolated South Pole. We've never seen one. It's not something that seems to exist. So back in 1981, just around when I was born, a graduate student, I believe, named Alan Guth, had been looking at these problems and was despairing. If I remember the story right, was despairing of his career in astrophysics and cosmology, and just had sort of an insight that if you just inflated space by a massive scale in a very short period of time, all of these problems just go away. So if the space part of the space-time continuum expands by 20 orders of magnitude early on, then all of a sudden everything is flat. You no longer have to violate the speed of light to have the temperature be the same everywhere, and you don't get any monopoles. And so the big problem that a lot of people have with inflation is that it really is a mathematical trick that is used to make the models line up, and there's no explanation of like why everything would have inflated. But it's very useful in making the model match our observations of reality. Now, there is something exciting about inflation. It's testable. So if inflation did happen, it would have actually caused an additional type of polarization in the cosmic microwave background radiation. So polarization is, if you look at sunglasses, if you look through sunglasses, you end up only getting light vibrating in one direction. If you take, say, 2 pairs of sunglasses, or if you have a lunar filter that is a twist filter, you actually can reduce, you can filter out light that is vibrating in different directions. And so inflation predicts that there's a certain type of polarization that is observable. And so we'll talk about that in a second. So just to get back to the flatness problem, the universe appears to be flat to at least 1 part in 10 to the 14th power, which is super, super flat. So just to indulge in a little dark universe, these are 3 different models for the end of the universe. Does anyone know what these mean? So if we have a curved space where all lines eventually converge, right? If you go far enough out in space, you'll always end up in the same place. Does anyone know how that kind of universe would end? At the end of time. Mike O'Dowd, I think, says collapse. So this would be called the big crunch. So this is where eventually inflation gives up, or eventually expansion gives up, and everything comes crashing back in to the singularity again. And so that's called the big crunch. How about the middle one, which is where 2 lines that appear to be parallel up close are going to keep diverging the further away you go. So it's a curvature less than 1, like a hyperbolic curvature. Does anyone know? No. So so this one is called the Big Rip. And what happens in the Big Rip is that space expands way beyond the ability of gravity to keep up with it, of electromagnetism to keep up with it, of the weak nuclear force to keep up with it. So basically what happens in the Big Rip, as it's called, is that not only does our galaxy get too far away from the Andromeda Galaxy to see it, not only does the Earth get so far away from the sun that light can't travel there anymore, not only do I get far enough away from Mike O'Dowd that I can't see him anymore, but also the electron of a atom in my body gets so far away from the nucleus that it can't see it anymore. And the actual protons and neutrons that make up the nucleus of my atoms get so far away from each other that they can't see each other anymore. So all of the fundamental forces stop working. So that's what the Big Rip is. So I'm glad that we don't have any of those. So Jim said the Big Freeze, and that's actually it seems to be the end of the universe that we're on track for. And that is where everything keeps expanding at the current rate, nothing changes. And eventually we just run out of energy in the universe and everything gets cold. And to quote Thomas Pynchon, turns into a gray salad of despair. So, the nice thing about that, it's still pretty depressing. But the nice thing about that is that it's going to take trillions of years to happen. So I'll take that over the alternatives. There's also something called false vacuum collapse. We're not going to talk about that, but it's scary. If you want some spooky cosmology, look up false vacuums. Yeah, so if you inflate space by 10 to the 50th power almost instantly, it enforces extreme flatness and the resulting expansion. If you inflate space by 10 to the 50 power almost instantly, then the temperature everywhere is the same without having to violate the speed of light. Because the inflation has gone faster than the speed of light, which I don't know if that's actually better. And if you inflate space by 10 to the 50th power, then monopoles created in grand unified theory also never happen. So inflation predicts also large-scale structure formation. It predicts the anisotropy that we see in the cosmic microwave background radiation, like the WMAP surveys of the sky. And it predicts that polarization I talked about. I think I copied this, but one alternative to this is just a variable speed of light. So that is kind of an alternative that is popular. A lot of people are looking into the possibility of that as a alternative to inflation. Unfortunately, that doesn't help with like the monopole problem. Okay, so this is kind of a visualization of what the polarization modes that we should see with inflation. So kind of the standard polarization mode is that we should see, vertical polarization parts of the sky and horizontal and other parts of the sky. But if inflation happened, we should see these kind of slanted polarizations as well. And I don't know if you have heard of the Bicep 2 observatory, which is an observatory down in Antarctica. So it's actually looking for this polarization. I believe that many of you remember in 2012, the Bicep 2 team announced very excitedly that they had detected it. I remember it being announced from this very podium that they had detected it and inflation was proved. Unfortunately, turns out what they had detected was intergalactic space dust that had very similar polarization characteristics to the what was predicted by inflation. So once they filtered that out, they were left with not much of a signal at all. And as of today, they just published some new results in 2020. So far, nobody is really very excited about what Bicep 2 has found. There are a number of other observatories on the way that may be able to observe with more precision. But once those observatories are in operation, if they don't find the B-mode polarization, inflation is going to be looking really, really endangered. So that's something that probably is going to happen in our lifetimes. So we should at least be able to answer whether or not that happened in our lifetimes. And if that did happen, that helps the Big Bang as a whole as well. So another problem with the Big Bang is, why is there stuff? Why do we live in a universe where there's stuff? I mean, one of the reasons is that if there wasn't stuff, we wouldn't be here talking about it. So, but there's a number of different explanations for why matter dominated antimatter in the final analysis. One of them is that maybe essentially matter is just more energetic than antimatter. This was actually proven in 1980 and it won a scientific Nobel Prize, but that alone is not enough to explain the difference. There may be an asymmetry in the weak nuclear force where matter is favored. That seems to be the leading candidate. One of the one of the kind of out there hypotheses that people had was that, well, maybe half of our universe is just antimatter and the other half is matter, and we happen to live in the matter part. But that doesn't seem to be the case. Like nowhere we look in anywhere in the sky do we see anything that looks like that. So we think that's probably not the case. And the most mind-bending one is maybe there's a mirror antimatter universe. I said there wouldn't be any multiverses, but this is the one. So maybe, on the other side of the Big Bang, there's an antimatter universe. And the only thing that is interesting about that is when we model, if you've ever seen a Feynman diagram that shows how a positron, an antimatter electron, gets emitted from a particular reaction, essentially the way we model positrons is as electrons traveling backwards in time. So it's an interesting thought, but I'm not sure if that is in any way reproducible. So I mentioned redshift quantization. This was something that a scientist named Halton Arp, who you may know from his catalog of weird galaxies, weird interacting galaxies. He thought that looking at the observations of redshift of quasars specifically, that there seemed to be groups of them, and that didn't make sense in a Big Bang universe. But what it turns out is that he just had a limited set of observatories to work with. In the intervening years, we have found quasars with all kinds of redshifts. So it's not really a thing after all. There's the question of fundamental constants. Wolfgang Pauli, the atomic physicist, said, "When I die, my first question to the devil will be, what is the meaning of the fine structure constant?" So basically, why are fundamental constants, like, are they constant? Do they change over time? Are they constant because we happen to live in a universe that supports intelligent life, and maybe different fundamental constants wouldn't support intelligent life? So maybe this is just the lucky universe that supports events like this. And that one, we don't have a good answer for that yet. Honestly, one of the areas that people are looking a lot at is the possibility that fundamental constants may vary over time. We'll talk about that a little bit in the alternative section. And then last year, the James Webb Space Telescope, you may remember this, found some galaxies that seemed to be too massive to have existed that soon after the Big Bang. And a scientist from Canada proposed that this meant that the Big Bang, that basically the universe would have to be twice as old as the Big Bang predicted that it was. More recently, an English university did a study of spectroscopic analyses of these distant galaxies. And what they found is that the yardstick we were using to measure the mass of these galaxies is not the yardstick that we should have been using, because it turns out that there were a lot more very energetic stars in those early galaxies than there are in galaxies today. And as a result, they were brighter. Basically, the galaxies were brighter than they would have been expected to be, which meant we thought they were more massive than they actually were. So that's one of the problems with using sort of a derived measurement, like a brightness mass relationship in galaxies that are not the galaxies you're used to. So right now, with the adjustments that they proposed, it does look like the 13.8 billion year number is still roughly in the ballpark, rather than 26.8 years, 26.8 billion years. All right, part that you've all been waiting for, alternative models to the Big Bang. So what was the view of the universe before the primeval atom hypothesis was proposed by Georges Lemaitre? There were two major different views. One of them was that the universe was static, that either it was spatially and temporally infinite, so it went off in all directions and lasted forever, or that it was that it lasted forever, but it had an edge somewhere. So if you went far enough, you'd get to the edge of the universe. It was not an expanding universe. And critically, and this is where it runs into problems, no new matter is created. And so the problem with that model is that it doesn't, seems like things would have run out sooner than they seem to have. And then the other one that was sort of more popular at the time was a steady state model. And that is temporally infinite. It is expanding. And in order to keep the density of matter throughout the universe constant, new matter is popping into existence. And so in quantum mechanics, we do, we do think in our real universe, new particles do just pop into existence. And those should be an electron and a positron, a proton and an antiproton. It should be matter and antimatter popping into existence. The problem with the steady state model is that in order for it basically demands that that happens a lot more often than we see it happen in real life. You would essentially have to have a Volkswagen and an anti-Volkswagen popping into existence. So that didn't make a very strong case for it. But one of the proponents of this model, Fred Hoyle, is actually the guy who gave the Big Bang its name. He was on a radio interview and he dismissively said, there's this Belgian priest who thinks that the universe started in a Big Bang. And for whatever reason, that is the name that stuck and is still the name we call it today. Now, there's another concept that just won't die called tired light. So it was first proposed by the Swiss-Hungarian physicist Fritz Zwicky as an explanation for the increasing redshift of distant objects. In his initial formulation, the idea was that the light basically lost energy as it traveled through space. In more modern formulations of it, the idea is often that electrons or photons that go through gravitational fields, photons that go through electromagnetic radiation may be slowed down. One problem with that is that if light did vary in speed in the universe that we exist in, like if it happened in real time, everything would be blurry, and we can look back at the very, very edge of the universe as we know it with the James Webb Space Telescope, and it's not blurry. So that doesn't seem to really line up with reality. And it also doesn't correspond well to the measured redshifts of supernovae. But for whatever reason, it just won't die. It was originally proposed as sort of an alternative to the Big Bang. It was more or less contemporary with the original proposal of the Big Bang. But nowadays, the more frequent use of it is actually to propose it as an alternative to inflation or to propose it as a modifier in a Big Bang universe. Here's one example. Lior Shamir is a professor in Kansas, at a university in Kansas. He actually was from the Department of Computer Science at Lawrence Tech. So I knew him in real life. So I still need to talk to him about this particular proposal and see. I've been trying to, basically his proposal is that if you look at different parts of the sky, galaxies that are rotating in one direction have different redshifts than galaxies that are rotating in the other direction, which is a true thing, but it doesn't necessarily have anything to do with the expansion of the universe. Because, but it's basically, if you look at the receding side, of the galaxy versus the oncoming side of the galaxy, you see a redshift on that side and a blue shift on the other side. But yeah. Anyway, tired light just won't go away. Varying speed of light, it is not an alternative to the Big Bang, but to the inflation process. This is probably the most active field of current research outside of sort of the inflationary Big Bang. And people are also playing around with other physical constants changing. The extremely ingenious mathematician Paul Dirac was very interested in the subject too. he noticed that there were just a lot of 10 to the 40th power numbers throughout the universe. And for instance, there's just a lot of weird coincidences, like the mass ratio of an electron to an average star is 10 to the 60th power. And Arthur Eddington actually was very interested in this too, the guy who sort of proved Einstein's special theory of relativity. He did some thought experiments in which essentially, sorry, the radius of the universe, you could kind of envision the radius of our entire universe as the radius of a hypothetical particle whose rest energy is equal to the gravitational self-energy of an electron, which is a very strange concept. But this was a very popular area of discussion back in the 1930s and 40s, and it may be coming back. Modified Newtonian dynamics is not an alternative to the Big Bang, but it is an alternative to dark energy and dark matter as a way of explaining things that we observe in the universe. Basically, it's that in large scales, the laws of physics that we know from Newton don't quite work the way that they do at the smaller scales that we see them. Now, one of the big problems with MOND is that when we look at the bullet cluster, so dark energy, dark matter, mostly we use to explain the movement of galaxies, but also like the bullet cluster has gravitational lensing that also supports the existence of dark matter. So modified Newtonian dynamics can explain the rotation or can model the rotation of a galaxy, but it can't explain the gravitational lensing we see in the bullet cluster. Tensor vector scalar gravity is another alternative to lambda CDM. The nice thing about it is that it can explain that gravitational lensing that we just talked about, but what it can't explain is like the structure of galaxies and the anisotropies that we see in the sort of web of galaxies. Loop quantum gravity is another non-alternative to the Big Bang. But basically what it is trying to do is sort of explain why inflation would happen. And also it sort of is a call for having a big bounce, which is where essentially the universe does collapse and then re-expands. A similar idea is the ekpyrotic or cyclical universe. And this is one that the string and brane theory people really like. This one predicts that in this cosmic microwave background radiation, there won't be any B-mode polarization. And this also is essentially a big bounce. So the idea is there's an endless cycle of the universe collapsing and then re-expanding again. And the sort of most recent wholesale model of the universe that is not a Big Bang universe is a plasma universe proposed by Eric Lerner based on work by Alphavin in the 60s. It predicts that it again basically predicts that there are Volkswagens and anti-Volkswagens popping into existence in the parts of the universe. It makes predictions that are observable, such as that there's going to be a large number of high energy photons. We don't see them. It doesn't predict things like the cosmic microwave background radiation, Hubble's law, or the abundances of elements in the universe. And so it doesn't do a super good job of making predictions that are testable. So it's still very popular among people who don't like the Big Bang Theory, but it hasn't really attracted very many researchers working on it because it doesn't do much to explain anything better. And that is last of the alternatives. So here's once again the family photo of the Big Bang. And I'd like to open it up to any questions. Let me turn some lights on this audience. Why doesn't it stop? All right, Ken.
The number of occasions we put back, the baryonic matter, the universe is about 5%. They're talking about dark matter being 30% or whatever the number is. So the rest is dark energy.
Right.
Does that relate to the fact that we have such a large universe? And what's the dark matter?
Yeah, so like the sort of the reigning model for dark matter is something called WIMPs, weakly interacting massive particles. Basically, it's the idea that there are these particles that we don't see, that we don't detect on any of our existing sort of sensors. They essentially like, so neutrinos are weakly interacting particles. They are passing through you constantly. If you want to detect a neutrino, you have to have a vat of mercury buried underneath the earth, and you have to watch for the mercury to move in certain directions. It's pretty crazy. The idea is that a WIMP would be something like that, but neutrinos don't have mass. So the idea is that dark matter would be something like that that does have mass. So essentially it's it's a particle that doesn't have any kind of electromagnetic force, that doesn't have a charge, that doesn't collide with anything, but nevertheless has mass, which is not something that makes a whole lot of sense to most people. Like it doesn't, so, there have been a lot of experiments aimed at detecting WIMPs, and none of them have found them. So essentially we've pushed the amount of mass that a WIMP could have down pretty far to the point at which they're not really explaining the apparent quantity of dark matter that seems to exist in the universe anymore. So I would say like dark matter is really in need of an explanation for why it has the effect it does, because we see something like dark matter in a lot of different ways, but we have no idea what mechanism it would work by, and we don't really have a whole lot of ideas beyond WIMPs. So, any other questions? Anything on the Zoom? Yes, sir.
Now, at the very beginning, when you had the antimatter and matter destroying the annihilating each other, that would seem to me you to release an incredible amount of energy. How did that even play with the Big Bang?
So keep in mind, like it's that annihilation is happening in an already incredibly hot plasma. So like it's definitely like adding energy to that plasma, but also at the same time the space is expanding. So I mean, that's an interesting question. I haven't read a lot of discussions of it. Um, it would be interesting to see if that's like taken into account in people's models of like how the temperature drops, because basically through each of these epochs that is ending with the annihilation of most of the stuff in the universe, the temperature keeps dropping anyway. So you'd expect that would increase the amount of energy in general, but yeah.
I hate to say this, some of us would like to make it to the restaurant before it closes. So are you planning to go to the restaurant or not, Jonathan?
I might sit at a different table.
We defer further questions to either right here now after we release people to go to the restaurant. With apologies.
All right, Jim, I'll take one from Jim and then.
I just suggest why make a big deal out of the fact that we can't detect dark matter? We just are using the wrong types of he likes his telescopes and stuff like that. We can detect it, and we do detect.
That's fair. I mean, we don't have a particle, like we really like having a particle and we don't have a particle for it. So, all right, thanks very much.
So already we meet next week at Macomb Community College, October 17th. Our next star party is Saturday, October 26th, and we meet after this at the Red Coat Tavern, Woodward, north of 13 Mile. Good night, everyone. Yes. There might be aurora right now. We're holding. Oh, I'm going to tell something when you